Hey everyone, this is Geo-Rant number 135, and today I'm going to talk about heavy minerals and sandstones. But first, it's about noon CST, which is -6 UTC, 33 degrees Fahrenheit out, so somewhere in between 0 and 1 degrees centigrade. But anyway, before I can talk about heavy minerals, because we do use them in sandstone analysis, they are important to a degree, although they are not heavily relied on as much as they used to be. And I am actually going to pull most of this stuff from a thesis I'm presently using as a reference, because I study the Frida sandstone and try to divide it out lithologically into other units, and it's called a field and petrographic study of the Frida formation along the Montreal River, Gogebec County, Michigan. It's Smale's 1958 thesis. That's where I'm pulling this list you're eventually going to see of heavy minerals from, well, most of it anyway. But first I need to explain what a sandstone is. First I need to say something about a sandstone. When we talk about what a sandstone is, it has everything to do with grain size, the individual grains, the size of the individual grains, and nothing to do with the composition. Okay? Nothing at all. If it's a sedimentary rock and it falls within a certain grain size, then it's a sand or a sandstone. And geologists, first of all, I want to say, as geologists, we usually use the Wentworth scale. It's a nice logical, logarithmic plot that makes sense. So I don't want any engineering comments at all. Okay, I'm not talking about USCS. I don't care. Okay, just nipping that in the bud before I go on to a side rant. But anyway, here's a Wentworth scale. And what you see here is you see in the yellow, this is where sand falls, which means sand-sized particles that make up sandstones. Above that, you have pebbles, cobbles to boulders, and below that, you have silt and clay, which we refer to as fines, because that's going to come back into play here. So basically, that's the Wentworth scale. So sandstone is grain sizes between about 0.62 and 2 millimeters. Now, how do we determine that? Well, we can do it visually, or we can run a sieve analysis. These are talks for other times, but basically, as long as it'll fit through one of these sieves, if you were to pound the sandstone back into sand or just the sand, if it fits through one of these, I have a set of these, the US sieves. You know, if it falls through one of these, it falls on that grain size. Okay, it's a little more complicated than that, but talk for another time. So you have your sandstone, that's what a sandstone is, but that's not good enough. We can divide it further, especially when we're trying to classify these things and decide their, their diagenesis, where they came from, their origins, things like that, their source areas. We start by dividing them into what we call aeronites and wackies. All right, so we have a sandstone, and they all are going to fall into one of these two. Well, what are these? Well, here you have an aeronite, which basically is a sandstone with less than 15% fines. Fines, what are those? Those are anything smaller than 0.62 millimeters, the silt and clay that I already showed you. And we have wackies, which are about 15% to 50% fines. And it has to do with textural maturity. There are other factors in determining whether a sandstone is mature or not, but this is where we start. Okay, aeronites are more mature than wackies. Okay, but can I have a wacky with more than 50% fines? Yes, I can. It's sort of a judgment call. Well, first of all, anything more than 50% is going to be a mudstone, like a siltstone or a shale. Now, in the rare cases, there's some rare cases where you can have a wacky that's 55% fines and still call it a wacky. Well, what would that be? Well, that would be if you had a wacky that had a lot of coarse grained sand in it, that very coarse, around that 2 millimeter mark. And as you can see here, you see something above here called very fine pebbles or granules. Sometimes, if most of the grains will be very coarse, some will be granules, we put those in with the very coarse. It's a judgment call on a lot of this stuff. But you want, if you call something a wacky with 55% fines, you want to be sure that someone in the field can identify it as a sandstone as opposed to a mudstone. Okay, and same thing vice versa. If a wacky's say 45% fines, you might just end up calling it a mudstone if it's a very fine or fine sand grains throughout all of it, because in the field, your eye is going to have a hard time picking out that very fine sand, all right, if there's a lot of mud in there. By the way, the very fine sand line, that 0.62 millimeters, that's about as good as the human eye can discern without magnification. That's why that's there, okay? But we can further divide out sandstones. Now we start getting into composition. There's almost any sandstone you see plotted is going to be plotted on what we call quartz feldspar lithic, or QFL diagram or plot. This thing, okay? All right? And it looks like this. Now they might be set up slightly different, but all of them have this much in common. They're going to have the Q up here, the F here, and the L here. This is quartz. That's primary quartz. You know, it's what you think of when you mostly think of a sandstone. You usually think mostly of quartz aeronites. Why do I have quartz aeronite on here and not quartz aeronite / wacky? That's because you'd be hard pressed to find a very mature quartz sandstone. This also has to do with maturity. Anything plotted, like quartz aeronites are very mature. As a matter of fact, the world standard for the most mature sandstone on the planet is the Ordovician St. Peter. Not only is it texturally mature, it's very well sorted, about as good as nature can get, which means grain sizes are all around the same size, which is the opposite of well graded in engineering. So nipping that in the bud too right away. Okay, so, and the St. Peter also has almost no fines in it. I think it's less than 3%. Okay, so anyway, this yellow area indicates that we have a quartz aeronite, a very mature sandstone. This means feldspars, that's the F, and that includes all feldspars, plagioclases and K-spars, or alkali feldspars, any of them. They all fall here. We don't discriminate between the two. And then your lithics, that would be broken down mechanical rock that you can identify, say, as not as a heavy mineral, because you're gonna have a hard time knowing what those look like, you know, without intense magnification. I'll get into that here. So this is broken down rock. This will be weird stuff. I tend to put chert in here. Some people put it here. I don't do that, but it's stuff like broken down volcanic stuff like that. Okay. Anyway, so you can take a sand. Once you know you have a sandstone, you can divide it into an aeronite or a wacky. And if you know how to, which just takes experience and practice, and my lab books go through how to do this, you can divide it compositionally as well. Okay, so what does all this have to do with heavy minerals? Well, because, and I didn't bring Bowen's reaction series chart with me, but that's okay, because it's still going to cover it here. Here's a list of heavy minerals. All right, you see this orange box here? These are minerals that are very resistant to chemical and physical weathering, okay? Which basically means once they form, that's it, okay? They're done, all right? And you have these, which are very susceptible to chemical weathering, okay? Olivine is very rare in igneous rocks on the Earth's surface, but common in the mantle. And why is that? Because at our surface and this environment, and a water, lane, oxygen environment, it's not stable once exposed. And here, these two, I said I was going to keep out weathering, chemical weathering products of these, but these are kind of in between. This appears in that 1958 thesis, but it's a rutile, okay? Now, why is this in yellow? Now, if you go through a sandstone, even a very mature quartz aeronite, now, you're going to find some heavy minerals. They're going to be usually less than 0.1% of the rock in total, and they're never going to contribute to the color of it. And you're not even going to probably notice them without detailed petrographic analysis, so they won't even be mentioned in the description. And that's fine, because for field use, it doesn't matter. But anyway, once you break out, you're going to find these, even though, where is it? Tourmaline forms, it forms at a much lower temperature in, say, a magma body than a zircon does. Zircons form first, and so do olivines, but zircons are resistant, olivines aren't. Tourmalines form at lower temperatures, but they're very resistant. Why is it? That has to do with Bowen's reaction series. Now, on the chart, it's a Y-shaped thing. I will link one below just so you know what it looks like, and we're going to deal with the left side. That's where you see these, and they eventually come down into muscovite quartz. Basically, Bowen's reaction series series shows you that if you have the right chemistry, certain minerals are going to crystallize first. These mafic ones, ultramafic ones like olivine, all the way down to the ones that are going to form last, like quartz. Now, the cool thing about that is they also weather in that order. So they'll crystallize in that order from olivine all the way down to quartz, but they'll also weather, chemically weather. These things like to be weathered into clays, and they will be transported downstream. So you don't really see these in clastic sedimentary rocks like a sandstone, but you will see these. And if you do see these, that means that the rock is probably near its source area. And even though it may be a quartz arenite and it's been transported, transportation of sand has to do with net transportation. A sand can be beaten along the same stretch of beach for 30 meters for 1,000,000 years, but it's had a lot of transportation. Or one sand grain can break off of a rock and go 100 kilometers away and isn't as transported as that beach sand was because it hasn't gone net distance as far. Okay, so if you see, but you're never going to see or I shouldn't say that. You're going to be really hard pressed to find a quartz arenite that has any of these. You might see this, but you're definitely almost never going to see these. But if you did, that would tell you that you're near the source rock. A zircon can weather out of a granite in Ontario and end up in a sand in the Mississippi, at the mouth of the Mississippi River in New Orleans. All right, and it's still going to be a zircon. Olivine isn't going to do that. It won't survive the trip. Does that make sense? Anyway, this is coming up on 12 minutes, so I think that's it. If you have any questions or comments, please leave them below, and I hope you learned something.